Okay. So exam 2, you all have got it. You've got it graded. Like I said, I haven't turned the grades on yet. I will sometime today, near the end of the class or so on and so forth. I am going to give you all a homework on steel. Okay. If I had to guess, you can probably expect 2 more homework assignments throughout the semester in here. Maybe 3. I'm not sure yet. But I'm definitely going to give you one on steel and alloys, because at the very least you need to process the data that we're going to collect on Thursday. And then I think you should do a couple steel related problems. I think it's really important. And I'm probably going to give you a homework 7. I'm not sure if I'm going to give you one homework on just wood and asphalt. I might split it up into 2, but I'm going to give you a couple problems on that, and that'll be our homework assignments throughout the semester. That'll be it. For Thursday, like I said, Thursday might be a little bit of a long day in lab, because we're going to be doing beam breaks, we're going to be doing cylinder breaks, and we're going to be doing alloy testing. So there's no way around that. That might take a little while. We'll talk about that more in detail on Thursday. One thing I will mention, on Thursday, bring your laptops, okay? We're going to do some data processing in class, and I think it'd be easier if we all do it together. So I will post a sample data file on Blackboard. We will all process it together. Sound good? Excuse me. Okay, I have that mentioned in the lecture today. It's like example 10, but we'll sort of skip it and leave that for Thursday. I kind of want to do it on Thursday because that's the day we're going to do it in the lab, and I think that makes a little more sense. Okay, we'll see if I have a voice in the next, between now and the end of the class. Okay, all right, so it's been a while since we've talked about steel, so let me sort of recap. Okay, so one thing I'm not going to cover is the production process. Again, I'm not going to talk about melting raw components or the metallurgy aspect or electric arc furnaces or anything like that. What I want to talk about today are commonly available steel products. There's a few things I want to get out of the way. We've talked about some of this before, but I want to make sure this stuff is clear. I want to talk about bolts. I want to talk about welding. I want to talk about rebar, because this is stuff that you all need to be aware of as civil engineers. So we talked about hot rolled structural steel products. One of the things that we said is that for structural steel, generally your carbon content will affect your yield stress, your tensile stress. It will not affect your Young's modulus in the world of structural steel. Regardless of your carbon content, generally your Young's modulus, the slope of the elastic region, is the same. It's not really affected by carbon content, so that's something to be aware of. But your grades of steel are going to be affected by that. We mentioned this last time we talked about steel, different grades of steel like A36, A992, A572, grade 50, and so on and so forth. I'm going to skip over this relatively quickly just because we've already talked about this, but I just want everybody to be aware that I mean, there's oodles and oodles of different steel grades. If you want a rough idea of which ones are the most common, I would say A36, A992, and maybe A572 grade 50. Those are arguably your most common grades of steel. Now, let me also say this. I'm leaving a couple out, like I'm not talking about rebar. Rebar tends to follow its own grade. And some other specialty products like shear studs tend to follow their own grade. Bolts tend to follow their own grade. But general structural steel, those are some pretty common grades that you would use. We talked about hot rolled shapes like flat bars, W shapes, angles, channels, T's, so on and so forth. Remember your terminology. This is the flange. This is the web. That's the flange too. This is the leg. This is the other leg. Yeah. So just make sure if you're talking about angles, it's legs of angles for I-beams, flanges, and webs. Just make sure you're aware of that terminology. Designations. Make sure everybody remembers this. So for a W21 by 93, the W refers to the shape classification. So this is a wide flange shape. It's essentially an I-beam, but we call them wide flanges because the flanges are flatter and a little wider in general. The 21 refers to about how deep it is. The 93 is its longitudinal weight. A W21 by 93 per foot weighs 93 pounds. So if I have a 10-foot long section, it's 930 pounds. So that's something that you as engineers should, you should just know that, okay? So that's just something to keep in mind. Angles. So the designation for angles, if I have an L 6x4 by 1/2, the long leg is 6 inches, the short leg is 4 inches, and each of those legs are a 1/2 inch thick. So if I had equal legs, I might say L 6x6 by 1/2, or so on and so forth. Everybody okay with that? Okay. So hot rolled products, they go into beams, columns, braces, girders, you name it. We mentioned cold form products last time that can be used for to produce decking or cladding or something like that. Cold rolled products are basically what happens is you take a pre-produced flat plate of steel and you successively bend it, into a desired cross section. So it starts out flat, and then you have one roller that kind of bends it up a little bit, one roller bends it up a little bit more, a little bit more, a little bit more, et cetera, et cetera. And it can you can get all sorts of different cross-sectional shapes with cold form steel. So that's a pretty commonly available product. It's very commonly used, for instance, in floor pans and deck pans for buildings. Like, how many of you have been on, here's another example. How many of you have been on a West Virginia DOH bridge construction site? Have you seen them use SIP metal deck forms for concrete decks? It's like a metal wavy pan. That's an example of a cold form steel. They also tend to be used for like wall studs in buildings, like light metal gauge wall studs in buildings. That's another common example application of them. They're really thin, so they can buckle, and because they're thin, if they corrode, it's a lot worse. So you have to take that into account. Okay, bolts. Did we talk about bolts last time? Okay, I'll sort of go over this very quickly. There are really three main methodologies to join steel together: bolts, welds, and rivets. We don't rivet anymore, okay? You may have to perform load rating or something like that on, let's say you have a bridge that's been in service for 50, 60 years, and it's got riveted connections, so you may have to do some sort of rating application to understand its capacity. Rating of rivets, rivets are highly variable in terms of their behavior, so and they're kind of dangerous to put in, so we don't use them anymore, especially nowadays since we have high capacity bolts and we can weld nowadays with a lot better quality control. We just don't need to rivet. So I really don't say much about rivets other than there might be a time in your career where you have to load rate them. And when you do, you basically make an assumption and apply one heck of a factor of safety to it. And that's pretty much what you do. I wish there was a more scientific means. There really isn't. There's been some research to try and quantify it, and it's very variable, so that's really the only way you can handle it. We tend to use structural bolts more often nowadays to connect steel elements together. Some common grades, arguably the most common grades of structural bolts are either A325 or A490. You can always tell the grade of a bolt by looking at the head of the bolt. I think it shows up a little better on the image on the bottom. When you look at a structural bolt, you'll see two symbols. You'll see A490. That is referencing the ASTM grade of that bolt. So you know how we've been using ASTM specs all semester? So ASTM, C33 for concrete or so on and so forth. If you look up ASTM A490, it is a specification for high shrink bolts. That's what it is. So those are your grades. A490s are a little bit pricier, but you can use less of them. So it's a question, if you have to design a connection, do I use 10 A325 bolts or do I use 8 490s? Well, it's a money cost, whichever's cheaper. So whichever's cheaper and whichever's going to be more available. There's never really a good answer to that. Steel is one of those materials where its price does vary a little bit from time to time. It's it depends. So you just need to be able to assess both. A307 bolts do exist, but we don't use those very much. Those are used primarily to like, get an initial connection together. They're used for temporary bolts, for secondary members. They're really not used very much in load carrying capacity. In your careers, you're probably going to see A325s more than anything, just so you're aware. Now, I'm not going to get too much into bolted connection design. If you have a chance to take steel design, we'll talk all about that. But I'll give you a few, nuggets of wisdom regarding steel connections. So if you're talking about bolted connections, generally when you design the connection, one of two things can happen if you're looking at failure. Either A, the bolt's going to fail, or B, the plate's going to fail. It's pretty much that simple. So if we're talking about bolts failing, it's pretty straightforward in terms of design. We determine, the limiting stress on, let's say, a bolt. So if it's an A325 bolt, we have a limiting shear stress. If it's an A490 bolt, we have a limiting shear stress. So we take that shear stress, multiply it by the area, and account for safety factors, and then we have the capacity of a bolt. So I'll make up a number. Let's say one bolt is going to fail in shear at 10 kips. Let's say my connection is going to have 120 kips on it. How many bolts do I need? If one bolt's 10 kips, the load's 120, how many bolts do I need? 12. It's that simple. Literally lay out 12 bolts. That's it. Make sure that you lay out your bolted connection according to spacing requirements and edge distance requirements. What do you think is going to happen if I lay out my connection and the bolts are too close together? What's the problem with that? What's that? That's a possibility. I'm thinking more practically. What happens if you got bolts that are too close together? Okay. There you go. You can't get a wrench around it. You have to have the bolts spaced some distance apart so you can actually put the damn thing together. Okay, now, what happens if your bolts get too far apart? That is possible, but that's not the more immediate concern. What do you do? Okay, what's the purpose of a bolt? Not really. Now, look, what are you using bolts for? You're using bolts to take one piece of steel and another piece of steel and slap them together, right? If the bolts get too far apart, I propose you're going to have a little bit of a gap. Flimsy's not the problem. What can get in there? Water. Corrosion. That's the problem, okay? Your bolts get too close together and you can't tighten them or you can't get a wrench around them. The bolts get too far apart and you're going to get water in the middle. So you just got spacing requirements. You got to make sure your spacing falls within the limits. So that's really, in terms of laying out a connection, largely that's basically it. For the plate failure, we really have two ways that the plate can fail. One way is we can have what's called bolt hole ovalization. The idea is that you're loading that plate, and so, you got a bolted connection, right? Got two plates together, you're yanking on them. So either the bolt's going to fail or the plate will fail. If the plate fails, you're either going to have what's called ovalization, where you sort of get some plastic behavior around the hole. It almost sort of acts like Play-Doh and it just sort of stretches out a little bit. Or you actually start to tear the plate out a little bit. So you just calculate both, take your worst case scenario. And as long as your connection has enough capacity to resist the loads, that's basically it. So that's the long and short of a bearing type connection. Now a slip critical connection is a little different. A slip critical connection, we have to ensure that neither of those things happen that was in the slide, but we also take into account friction, okay? So here's a plate, here's a plate. Slap them together, stick a bolt through them. More you tighten that bolt, what's going to happen to the two plates? They're going to push together, right? I'm going back to physics 211. I got a normal force. I got a coefficient of static friction between plate A and plate B. That means that there is some frictional force developed between the two plates, right? Okay? I can count on that for design purposes. Now, I can't get as much capacity out of a slip critical bolt than I can a bearing type bolt. So if a bearing type connection only needed 10 bolts, slip critical connections might need like 20 bolts. Okay? But that might be necessary in certain considerations, in certain scenarios. For instance, if I got a lawnmower and I've got the motor bolted to the frame and it's really loose, I start that lawnmower up and I start running it, what's going to happen? Those bolts, this is going to fall off, right? So under any scenario where you're going to have either vibratory loads or any scenario where you're going to have high cyclic load, you kind of have to use a slip critical connection. Now, what civil engineering applications do we deal with where we have high cycles of loads? What's that? Bridges, yeah. So generally, connections in highway bridges are slip critical, okay? Now, to get a slip critical connection, you have to install it a certain way, okay? The first thing you have to do is you have to get the bolt snug tight. Now, what's snug tight? How do you measure that? Well, generally, snug tight is a few hits of an impact wrench or the full effort of an iron worker using an ordinary spud wrench. Literally just getting the plates into contact. Okay. Once you've gotten it snug tight, you have to use a prescribed method to actually get the prescribed tension in that bolt. We're talking each bolt can be seeing 10, 15,000 pounds in pre-tension. I mean, we're talking about significant tension here. We're not talking about just getting it kind of tight. I mean, these are prescribed tensions in order to generate that that required frictional force. Now, there's a couple ways of doing that. One of the simplest ones that you'll see is what's called the turn of the nut method. I'm curious if you've ever been on a DOH construction site. Did any of you were any of you on a site that involved a steel bridge? Were the elements spliced together? Did you see chalk marks on the connection that looked like this? Okay, this is what the turn of the nut method is. So the idea is that depending upon your bolt and depending upon your connection, you'll look it up and you'll see snug tight plus, I don't know, a third of a turn, or snug tight plus a half of a turn. So what you'll do is you'll mark your bolt, mark your plate, and let's say it's a half a turn. So you'll mark this, but then you'll mark your nut half of a turn away. Then you'll apply that tension to where they line up. When it's all said and done, all of your bolts and all of your nuts should line up. And that's an indication that you've got the appropriate amount of pre-tension. Is it a rough estimate? Yeah, it's a rough estimate. But generally, if you actually measure the required pre-tension in volts versus what we specify, we usually end up getting a little more. So that tends to be not a big deal. This is one way of achieving a required pre-tension. Another way is to actually use just a calibrated wrench. So if you're on a construction site, if you ever see one of these things mounted, it's called a Skidmore Wilhelm. The idea is you put a bolt through that Skidmore Wilhelm and you use a calibrated wrench, and this thing basically has a dial gauge and it reads how much tension you're applying to that given bolt. And you use that to calibrate your wrench that you're installing the bolts with. Now, once you stop using it and go take a smoke break or something, guess what? You got to go back and recalibrate it. So when you get it calibrated, just keep using it until you're done. So just a piece of advice. Yes? Effort. Usually, I mean, you'll need a larger bar wrench. There are some high-capacity power tools that you can use and just work in it. Well, let me say this. One method that's become real common nowadays is to use twist-off control bolts. There's a little bit of an initial premium because you have to buy some special hardware, but they're really nifty, okay? And they're really simple to install. These things are pretty cool. So first off, if you ever see a twist-off control bolt, one of the things you'll notice is that the head is rounded. Okay, which if you've ever put things together, if you've ever done any mechanic work on a car, you're like, well, don't you have to have a hex end on each end so you can put a wrench on one end and a wrench on another end? Like, how do you grip that? Well, you don't. Okay, this is a very specialized wrench, so let me explain how it works. So you put the bolt through, you've got your washer and your nut, you screw that on. What this specialized wrench does is it actually grips the nut and the bolt at the same time. So if you notice, see how there's this sort of nub on the end of the bolt that's got these little grips on it? Everybody see that? So what the wrench does is it grabs that splined end and it also grabs the nut, and it turns them both at the same time. And then once you reach that required tension, it breaks it up, breaks that end off. So all you have to do is look at the connection, and if you see a bunch of connections with those ends broken off, you know you've met your required tension. So it's a little easier on an inspection side. A lot of contractors tend to like this because it's quick. You can do it done, get it done. So, anybody ever seen this used? You seen it used? It's pretty nifty, isn't it? What's that? Oh, the one in Charleston? That doesn't surprise me because there's a lot of bolts there. there's a lot of connections there. And I mean, you're talking about serious savings of time. I mean, real time savings. That's the type of stuff that wins bids. You know, if you say, well, I'll use these connections as opposed to standard bolts. Is there a little premium, a little bit more of a premium? Yeah, but how much labor are you saving over the entire job? That's serious savings. Okay. Any questions? All right. Now, let me just make sure you all are aware of something. Okay. We could all go out right now, and as long as we had proper safety training and the appropriate tools, everybody in this room could be installing bolted connections right now. Okay? That's bolts. Welds, yeah, that ain't the case. Welding is an art form, and it takes years to acquire that skill. How many welders do I have in here? I'm just curious. Okay, so we got some folks in here that can weld. Welding is not easy. It's not something that you pick up and within the first 5 minutes you're an expert welder. There's a reason that welders who do welding on nuclear submarines, there's a reason that they bring the paychecks home that they do, because it's tough. It's not easy, okay? So it's something I want you to recognize. Welding is an art, okay? Now we can get some serious capacities out of welds as long as they're done appropriately, hence why the required training. I can take piece of metal A and piece of metal B and join them together. That's all I can promise you. I can't promise you an AISC certified weld. I'm meager at best. So yeah. I mean, I can weld, but I'll be the first person to admit I'm not great at it. There are oodles of different ways to weld, but generally I want to cover the two primary means of welding, and you all, and those of you who weld know exactly what I'm talking about. There's stick welding and what else? MIG welding. I mean, now there's TIG and all this other stuff, but we're talking about civil engineering applications. Stick and MIG welding are generally the most common. Now, just so everybody's aware, okay, you are not gluing two pieces of steel together. That's not what you're doing when you're welding, okay? You are literally melting this consumable electrode and creating a molten pool of metal. So you have, piece A, piece B, and the weld metal, and melting those together into a solidified joint. Doing that at an appropriate pace, at an appropriate temperature, with no porosity, that takes skill. So stick welding is one of the most common. I'd say one of the big differences between stick welding and MIG welding in terms of actually designing a structural joint. Stick welding tends to be used for more high capacity joints. MIG welding, on the other hand, is for littler things, smaller things in the world of civil engineering. The difference between the two, stick welding, you're using a repeated series of consumable electrodes. There's weld sticks that start off about like that. Then you're consuming it as you go, grab another one, so on and so forth. MIG welding is a little simpler, I think, because first off, you're using a continuous spool of electrode. So if if you're checking out, if you've got like a garage back home, you probably are more than apt to find a MIG welder than you will a stick welder. But in large civil engineering applications, stick welding's, I think, a little more common. One thing you have to be aware of with welding in general is it's not just the metal consumables that you have to control. You also have to control that atmosphere right around the welded joint. You do that with one of two ways. You either have a gas shield that you have. So if you ever see a large application, you'll see your weld wire, but you also see like a big tank of gas shield that prevents hydrogen embrittlement in your weld, or you use a flux cord wire. if you ever use a flux cord wire in your welding, you'll know it right off the bat, because when you finish welding, there's this white soot stuff that gets collected on the welded joint. You kind of have to chip that off. But the idea behind those shields is they're trying to eliminate the ambient hydrogen in the atmosphere. Hydrogen gets into a weld, that's bad, because it creates embrittlement, which creates a weld that's more susceptible to cracking. So we try and avoid the hydrogen. I'll talk to you a little bit about some different types of welds. So what's the first weld that you ever apply? The tack weld, right? That's the first weld that you do is a tack weld. Tack welds are not structural in any way, shape, or form. They are there to get the piece where it needs to be. So here we have a clip angle on a wide flange section. So the idea is here's the beam. This is the connection. This would then be bolted onto a column in a building. The first thing that you do is you do a tack weld. Just a couple quick hits of your stick or MIG welder just to get that in place. So you weld it, and then you do a whole bunch of measuring to make sure that that piece is where it needs to be. If you're wrong, well, you can grind that off. You do not want to fully weld that entire connection and then find out it's a couple inches off. That would be a bad day. Break out the grinder and start doing some grinding and cut that thing off. That's the only thing you can do. So tack welds are the most common, or they're performed on just about every welding application. Most common structural weld is a fillet weld, okay? So a fillet weld, we're talking about finished structural welding joints, okay? A fillet weld is the most common. I'd say 85 to 90% of all the welds that we use in civil engineering are fillet welds. So what do I mean by that? I'm talking plate A, plate B, let's say going like this, and filling in that welded joint. That's a fillet weld. When we compute the capacity, the idea is, we have a plate, so we assume our weld, looks something like this. So here's our weld. So for a capacity check, we take the length of that weld, however long it is along the element, we multiply that by this distance. That's what we assume to be our worst case scenario from the root to the face. It's the shortest distance that defines the capacity of the weld. For my steel folks, you remember what that's called? You remember what that distance is called? It's the effective throat of the weld. You should remember that. I should have said, Dr. Mike has a sore one of these today. I have a sore throat today. Yeah. That's not tweet-worthy, though, so that one wasn't very tweet-worthy. All right. Fillet welds are the most common. The second most common, I would say, are groove welds. And groove welds are really meant to just completely splice plate A to plate B. There's not really much design from a structural standpoint, because all we do is we say, okay, let's design this so that the plate will fail before the weld does, and let's just fill the damn thing with weld metal. That's, in terms of capacity, that's pretty much it. So if you take steel design, fillet welds are what we spend the most time designing. Okay. Any questions on connections? We got bolts and welds. Those are the two main ones that we use. Any questions on that? This is good stuff. So, okay. So considering, I know reinforced concrete design is being talked about next semester. Let's talk a little bit about rebar. Okay. So rebar is I would say if we're taking wide flanges and angles and channels and stuff like that off the table, rebar is by and large the most common steel product that's used. I mean, if we're talking about a superstructure, let's say for a building, it's either going to go steel or concrete. If it goes concrete, it's going to have rebar in it. If it goes steel and your floor system's a big concrete slab, guess what? There might be some rebar in it. So rebar is very, very, very common in civil engineering. So I want you to be aware of the products, what's available, etc. Okay, so with reinforcing steel, rebar is obviously the most common. We can also use welded wire fabric for some applications. We'll talk about that here in a second. All right, so rebars are generally described by their grades. Grade 60 is the most common, and what that means is if I say I'm dealing with grade 60 rebar, I'm talking about its yield stress. So yield stress, so grade 60 rebar, its yield stress is 60 KSI, or 60,000 PSI. Y'all remember what yield stress is, right? That's the point when it stops behaving like a rubber band and we start getting permanent deformations, right? So that grade 60, more often than not, is the most common. Now, rebar sizes, okay? Y'all ever heard the term like number 4 rebar, number 5 rebar? Y'all know what that means? Good, because that's what we're going to talk about. Okay, so I'm going to skip this because you all have this. Just additional grades of rebar, but A615 is the most common. Okay, rebar sizes. This is something I want you to remember. Okay, if I want you to remember what a W10 by 49 is, I also want you to remember what this is. So let's talk about rebar sizes. If I say number 5 rebar, what does that mean? That means anything from number 3 to a number 8, we're talking about the diameter. So if I say number 5, the diameter of a number 5 bar is 5/8. That's what that means. So number 7, 7/8. What's the diameter of a number 4? 4/8, or 1/2. Make sense? Everybody okay with that? Now, so that's number 3 to a number 8. Number 9. Number 9 is special, okay? A number 9 bar, if I samurai sword or lightsaber through it and I look at the area, a number 9 bar has an area of 1 square inch. Exactly. Now, its diameter is like 1.128 or something like that. The idea is what diameter is required to get exactly 1 square inch. That's what a number 9 is. Number 9s are very, very common on the FE because you'll have some reinforced concrete problem and it'll say, determine how many number 9s you need, to design this beam or so on and so forth. And you do the math and you say, well, I need 4.5 square inches of steel. How many number 9s do you need? You need 4.5 of them, so use 5 bars because the area is 1. Something to keep in mind. The number 10, numerically, the diameter and the area are equal, and then the number 11, number 14, and number 18, those are just really big bars. So yeah. Any questions? So what's the diameter of a number 7? There we go. It's like we're going to talk about that on a celebration or something. Why is he going on about this? just something to think about. Okay, if you ever look at a piece of rebar, you're going to see various markings on it. Y'all ever seen these before? Let's talk about what these mean. Okay, so generally you're going to see 3 marks. Sometimes you may see 4. The first one right here where it says H, that refers to the mill that has produced that steel. So each mill has their own symbol. I think we're using H here because unless I'm mistaken, I don't think there is an H mill. So it's like this is just a generic one. So the H refers in this case to whatever mill produced this. The 11 refers to the size. So this would be a number 11 bar. And then, the grade, so grade 60, or the S for the type of steel. So that's something to keep in mind. Maybe I'll show you a picture of rebar on an exam and say, tell me what's up. So, sound good? Okay. Welded wire cover. This tends to get used a lot for shear reinforcement in beams. It also tends to get used a lot for floor slab buildings, because floor slabs in buildings, they don't really see a lot of load, so you don't need to go overboard and use these big humongous pieces of rebar. You could use a little bit of steel spread out over a long distance and it would do just as good. Another thing if we're talking about like slabs in buildings and stuff like that, it's not really so much structural capacity that we're worried about. What we need to place enough steel in the slab just to prevent it from like cracking under thermal conditions or under day-to-day use. So that's another condition as well. Just so you're aware of the terminology, the first 2 numbers, the 6 by 12, so the 6 refers to longitudinal and transverse wire spacing, and the 16 by 8 are the areas of those bars in hundreds of square feet, or hundreds of square inches per foot. So it's pretty straightforward. Okay, what else do I have? Okay. One other thing that I did want to mention is pre-stressing strands. Pre-stressing strands are a unique animal in and of themselves. If regular old rebar can withstand about 60,000 psi before it yields, this stuff like 270,000 before it yields. This stuff is high grade, expensive steel, but it needs to be because of its purpose. I mean, we're trying to slim down large load carrying capacity elements for buildings and bridges. So the idea is we lock a lot of force into that steel, and it'll reduce the amount of force in the concrete so we can slim up the beam. Because of that pre-stressing steel, it tends to be pretty high capacity stuff. Let me see something real quick. We've got testing of structural steel, and then that's it. Okay, I think what I'm going to do is this. I think I'm going to call it. What we're going to do next time is this. I want to give you all a taste of things to come for next time. So, okay. One thing I really want you all to be able to do is interpret one of these, a stress strain curve. And one of the best ways that I think of interpreting a stress strain curve is to make one. Okay? What I mean by that is this. We go down to the lab, we're going to take a piece of steel, we're going to yank on it, we're going to fail it, we're going to take that data, and we're going to compute a stress strain curve. We're also going to do the same thing for brass and for aluminum and some other materials. But I want to teach you all next time how to take that data and actually convert it into usable stress strain data. So next time, what do you bring into class? There we go. With Excel. I need Excel. That's what we need. So, also, next time, be prepared. Lab may be a little long. So, just be aware of that. That's all I got, guys. I will see you all on Thursday.